Okay, happy Monday, everybody. Any questions about assignments 1, 2, or 3? Before I jump in. So assignment 1, I'm making good progress. I'm assessing those. I have 10 to 15 left, which is quite good for 1 week. So I'm on target to have them completed by Friday. I'm on target. I can't predict the future very well, but I'm on target. Basically, when I look at those assignments and I'm assessing them, I can put them into 2 piles. Attends lecture, doesn't attend lecture. It's pretty straightforward. So if you give me a coursework, I can put them in one of those 2 piles. Yeah. Or I could rename the 2 piles attends lecture or watches lecture. Or doesn't attend lecture and doesn't watch lecture. So I can make them a little bit more descriptive. Yeah, I think that's... Oh, and the other thing is I'm trying to prepare the exam for this module this week. We're supposed to have our exams prepared by Friday for all the modules. So I'm thinking of test questions and things like that. And I'm going to introduce some new questions. I think the past tests could be more exciting, could be a little bit more fun, could be a little bit more difficult, or like kind of a little bit more challenging. So I have a collection of past exams, and it's like there needs to be a little bit of it's an injection of some fresh angles, let's say, and yeah. So I'm trying to be a little bit more. I think creative is the word I'm looking for. I'm trying to introduce a little bit more creativity in there. And the first question is definitely more creative than typical first questions in past exams. And hopefully that will be true about the second and third questions. Okay, I noticed when I use that word exam, everybody immediately is quiet. That's a good trick, like I need to remember that.
Anytime anybody talks about an exam, it's never because they're going to say, oh, the exam's going to stay exactly the same as last year, so it's going to be really easy. It's always like an overall making it harder. Last exam, people scored too high, so this year, it's always like that, every time.
Yeah, I understand. Yeah. Okay, so today's discussion is not going to be trivial. I'll just mention it again. It's a non-trivial subject. There are just kind of difficult aspects to understand, but given some time, hopefully you will understand this. This is the theory. It's kind of funny because in data visualization we present the theory, but actually the theory is very... It does talk a lot about implementation too. So it's not like pure theory because you see real images and real algorithms there. But assignment 2 is really like, okay, let's take the theory and put it into practice. Just like assignment 1, right? The assignment 1 was taking the InfoVis theory and putting it into practice. Yeah. So assignment 2 is that kind of thing that style is very apparent in both parts of the module. Okay, so last time we talked about lots of terms, introduced new terms, raycasting, different ray functions, 4 different ray functions, more terminology, classification, more terminology, transfer functions, and some different transfer functions, gradients, terminology, and 2D transfer functions, so 1D versus 2D transfer functions. So today we're going to talk about the raycasting pipeline. We love pipelines in this module. I guess I'll start off with a question then. Does anybody remember the pipelines we talked about so far? In my mind are the previous 3 pipelines.
Database, voltage, or were those the frameworks?
Yeah, you're right, but I wouldn't say those phrases exactly. Where's the attendance register? Hiding? Reluctantly passing it back. Yeah, so you said data viz, vol viz, right? Is that what you said? That's 2 of them. So one's just called the visualization pipeline. One I call the volume visualization pipeline. There's another one though that I didn't really call it a pipeline, but it looks like a pipeline and you can think of it as a pipeline. It's that knowledge evolution, the ubiquitous pattern of knowledge evolution, which you could call a knowledge pipeline. So those are the first 3 pipelines. And why do I mention that? It's because they're all related. All 3 of those are related. And this is also related. They're all related, and the viz pipeline is very general, and then the vol viz pipeline is a little bit more specific, and this one is even more specific. In some ways, they go from most general to most specific so far. Before we jump in, this one's for Rodri, even though he's not here. Raycasting versus ray tracing. So I think a lot of you have heard of ray tracing already from your amazing computer graphics module. Ray tracing is a computer graphics technique, and raycasting is a volume visualization technique. And remember, we make a distinction between graphics and viz in this module. Does anybody remember that distinction from way back? And that would be an interesting test question, actually, now that I think about it. Anybody remember that what we said the distinction was from the first lecture? That is a tough question just to knock you out on the mind that you made.
Yeah, it's like computer games showing made up stuff.
Exactly.
It's to show data, like meaning time.
That's right. So computer graphics is concerned with fiction, and data viz is supposed to be concerned with non-fiction. So you can associate that here too. I mean, you can make that association. Ray tracing is associated with fiction, and raycasting is associated with non-fiction. But ray tracing is a method, it's an algorithm to compute accurate lighting and shading of a scene, of a 3-dimensional scene usually. Right? And the input to ray tracing algorithms is a set of triangles or a set of surfaces composed of triangles. Right? And the rays, so they're both image order techniques, so that's something they have in common. Another thing they have in common is they both use rays. So in ray tracing, you cast in a ray, for each pixel you cast a ray into the scene, and then you sample the scene, you sample the surfaces of the scene and the light sources to find out where the light sources are coming from, right? So you sample the surface, so you're sampling the environment in order to compute accurate lighting and shading. And that tests your, like in ray tracing, the computation hinges around detection of intersections. So you're always asking this question, which surfaces does this ray intersect? That's the central question, and that's what the computation hinges around. Carlo?
In ray tracing, don't you calculate the refractor in the as well, the rays basically.
That's right. So there's more than one ray. So or what we call a primary ray, the first one, and then if it reflects a secondary ray and maybe a tertiary ray, the next term.
Basically, in raycasting, all the shading effects and everything comes from the fact that there's real shading, real data, while in ray tracing you're just making it up because it's not real.
It's the shading in ray casting is also synthetic. So you may have noticed from the marching cubes algorithm that it's a synthetic kind of shading, but it's supposed to reflect reality. But there's no light in a volume viz data set. There's no light. There's no light source. It is necessarily, right? You just get an input of 3D data. That's it. So the input to ray tracing algorithms is a set of surfaces on triangles, and the input to ray casting algorithms is a 3D volume data set. So those are different. The computation, the intense computation with ray casting is involved with sampling the data along the ray. It's not concerned about does this ray intersect a surface. It's what data am I encountering along the way and how do I sample that in an effective and efficient manner. That's the central, that's the focus of the computation generally. And then there are shading effects you can apply afterwards, so to speak. Yeah. So those are some of the differences between ray casting and ray tracing. And ray casting is only concerned, generally speaking, with the primary ray, so the one ray that's cast from each pixel to the set of voxels that it intersects. Yeah, and if anybody's curious, that was a question for a test. Somebody was asking that question for a test in database, and so I made a YouTube video like that does that question in great detail with a table, 3 columns on a table, everything they have in common and everything they have different, and so on. Okay, so this is kind of, everybody knows this already because we've kind of covered it already, but this is just a little bit of background data. So the volume data, the input is a set of 1D values defined in 3D, right? So this is a volume data set, and there are data values along every dimension, X, Y, and Z. A ray is cast. Actually, if you want to get technical, this is a half ray, because it has a starting point and then exit, so to speak. If it was a pure ray, it wouldn't have a starting point. It would just be infinite in both directions. It's not important. And the ray's job is to sample the data along the volume to find out what data samples it encounters. Right. And here is the ray casting pipeline, or a ray version of the ray casting pipeline. So now, hopefully you can, this is not completely different from the viz pipeline or the whole viz pipeline, right? They have some things in common. So the input is a set of voxel values. That's just basically like the data acquisition and data enhancement phase. It's after the data enhancement phase of the viz pipeline. So the input is a set of voxels on a 3D space. Now, each of those voxels, for every voxel, a color, an RGB color is assigned based on the data value, and an opacity is assigned also based on, well, in this particular algorithm, it's based on the gradient magnitude, right? So for every voxel, we assign a color and an opacity, right, to the input data. Then the next stage is a processing stage, right? The raycasting or raycasting processing stage. It's a sampling stage. It It's that stage where we shoot a ray into the volume and then test to see which data values we intersect along the way. And from that, we assign we have sample colors, right, for each ray, and sample opacities along each ray. And then there's a projection phase, just like in the Viz pipeline, there's a projection phase. And that is called compositing. So you have a stack of colors along the ray, and you have a stack of opacities along the ray. And then you add them all up. You project them from 3D space to 2D space. And you end up with a set of pixel colors. Pixels have 4 properties, right? Red, green, blue, and alpha values. The alpha is the... Anybody know what the alpha is from a pixel? From your computer graphics class?
Is it to do with transparency?
Yes, yes. Or the inverse of opacity. So that's the basic pipeline, and the rest of the slides are just talking about these things in more detail. Right? Each of these steps in more detail. Just like we did with the Viz pipeline and the Vol Viz pipeline. It's like a circular... At least it's not random, right? That would be stinky. So, the shading and classification of voxel values. So you've already seen this. Anybody? This is a great example of aliasing, right? These are supposed to be straight lines, right? It's a perfect example. It's kind of fun. So the voxels are assigned colors and opacity, every voxel, right? According to a transfer function. That is a little bit of Greek just to make things more interesting. I'll fix that before, after the lecture when I upload them onto Blackboard. But along this axis we have voxel values assigned to color. And then along this axis we have voxel values assigned an opacity based on their gradient value. Right? And this is supposed to be like a pyramid kind of shape, or a 10 kind of shape. And as this ramp goes up, the opacity goes up. So this is gradient magnitude going up. And this is opacity going up. So the idea is, as gradient magnitude goes up, opacity goes up. In other words, we see the gradients, or the changes in the data, the sharp transitions. We're trying to highlight the sharp transitions automatically, right, without really user involvement. And that's the idea. So that's step 1 of voxel color assignment and voxel opacity assignment. Right, now you can see why we mentioned this classification, right? Because that's good for color assignment. Now the sampling, we've never talked about this yet. I think this is the first time we talked about sampling voxel data using array. This is the first time. So here are 3 different ways. There are more than 3 different ways, but here are 3 basic ways to sample volume data using a ray. So remember, the rays are cast from image space into the volume. So image space is over here. And this one is called regular sampling. So that means we hit the volume, we sample the volume at that position, right? We derive a value, a scalar value. Then we move a fixed distance along the ray and perform the sampling again. We move at exactly the same fixed distance along the ray and sample again and repeat. So the space between samples is fixed, it's uniform. Here's a simpler one where we have an array and we just take the value of the voxel from the center. we can compute a derivable. We just take the center value. So we find out which cell we're in, and we just take the center value. Center value, we derive which voxel we're in, and we always take the center value along. So the space between data samples is changing there. It's actually changing because we're always using the center. Even though these are uniform here, the value we're using is from the center of the voxels. Right here, here. And now these three are uniform, but look, the distance between these two is jumped. Right? This distance is shorter than that distance. And you have this kind of staircase-ish, an exaggerated staircase effect or aliasing effect. And then you have a third approach that is based on voxel intersections. So we cast array into the volume. We find out, we take a sample whenever we hit the edge. Whenever we hit the edge of a voxel, right? That's not very difficult to detect because the voxels have a fixed width, right? So we know whenever we're going to hit the edge of a voxel. We take a sample every time we hit an edge. So here there are two edges close together where the ray intersects. So we have two close, then two farther apart, and so on. Now the question is now, like, why do we have these three different sampling techniques? Anybody want to take some guesses at that? There must be, well, there are more than three, but here are three to start with. Is it Jonathan? Liam.
Performance, like, you might have a lot of interceptions as opposed to like a separate.
Yes, you have the right idea. It's always, well, this is true about all of computer science, not just biz, but there are always three trade-offs. In this case, there are just the two, really. But in all of computing, there are three trade-offs. Speed, computing speed, accuracy, and memory, how much memory you occupy. So if you're increasing speed, you're lowering accuracy or memory, or increasing memory occupancy, memory footprint. Right? You can decrease the memory footprint by decreasing accuracy and speed. Or you can make something super accurate, but it costs in terms of it slows things down. Or maybe it costs more memory. So you have these three things, and one bar is going up, and then the others are going down. And when you publish a research paper, you just talk about the one bar going up, and you try to make everybody ignore the ones like that are getting worse. But here's the same story. It's mostly performance versus accuracy. So here we have really an accurate sampling because we have unit distances, equal distances along the ray, but the performance is going to be the slowest due to the number of interpolations. Here we have one interpolation, but here we have three interpolations. I have to put down my T. Here we have three. To get this value, we need to interpolate here, here, and then here. That's three. And in 3 dimensions, that's 7 linear interpolations. To get here, we have, because if the values are stored at the voxel corners, it doesn't matter. They could be stored in the centers. The result is the same. We would have to interpolate once, twice, thrice to get that data sample. Right, three linear interpolations. Here it's just one if it's on the edge, and so on. So there's a lot of interpolation that's done. Right? It doesn't matter if the data is stored, it's the centers or the corners. It's still the same challenge. If it's at the centers, we still have to do 1, 2, 3 linear interpolations to get the sample value we're looking for. Here, no interpolation, just take the center value or whatever you want, the value of the voxel. But you might have some aliasing, right? Because sometimes your sample distance is a little bit big, relatively big compared to the other ones. So that's fast, least accurate, most accurate, but the slowest. And then this is like a compromise in between. The interpolation is easier here because it's always one interpolation. 1, 2, 3, 4, 5, 6. So it's always one interpolation for every data sample, as opposed to 3 or 0. So there's a compromise, and you don't have a jump. There are no big jumps. What you might have are a few extra, but there are far fewer interpolations than the first option. And there are more sampling strategies. They're not just those 3, but those are 3 kind of basic ones. Yeah. Carlo?
So the regular sampling would be give the most uniform result. Right?
Yes, yes.
Time conversion gives hue difference basically. So
That's the fastest. Yep.
In the Voxel intersection, do you keep the same like color? Like, could you have like a aliasing in opacity or something like that? But when you interpolate once.
You probably aren't going to have aliasing artifacts, but you have these extra samples, and you have a little bit less control over the accuracy because you're constrained to these edges. Here, you can adjust the distance to whatever you want. So if you want higher accuracy, you just adjust the distance to something smaller, the uniform distance. Here, you don't have that option. You're stuck, so to speak. You're confined, you're bound exactly to the width of the voxels.
So wouldn't the regular sampling be the most versatile one?
So basically, the answer in that case is almost always the same too. You want, when you're actually writing Viz software, you want basically 2 options, maybe 3, but 2 generally. One is fast for exploration and interaction, and then the other one is very accurate for presentation and analysis. So depending on what you're doing. So if you want to just explore what's happening, you offer a fast one. Like, you just open the volume data and you just want to rotate it and just see what's going on.
But if you increase the distance of the first one, that's still be slower than the other ones.
It depends on how far you increase the distance. Yeah. Because every one of these samples has a cost associated with it, right? So here, the cost is in the middle, here it's the lowest, and here it's the highest. But at some point, you know, if there's a trade-off, so at some point, if you decrease the number of samples here, at some point it's going to be the same performance cost as this one. I don't know exactly when, but you have to count partially the number of interpolations. Right? When the number of interpolations is equal, then you'll have something similar in performance cost.
And would that be reflective accuracy as well?
Yes, so in this case, you would get something that's not very accurate because you'd have to get double the distance between the samples to get the same.
What I mean is, if we take regular sampling in Voxel intersection and make it at the same cost, would the accuracy be similar or comparable? Or there's one point in which the other algorithms actually just perform best?
Have you ever heard of the Nyquist limit?
Yeah, isn't that the one about poor performance?
You're the signal processing guy. So I'm going to spam you back. So the Nyquist limit is, so Carlo's asking a lot of questions about accuracy. Like, And the accuracy is tied to the Nyquist limit. And that's a signal processing theory. Does anybody know, already know that term? It's something you would have to know if you were in electrical engineering, the Nyquist limit. It means that to reconstruct any signal, as in Carlos' third-year project last year, you need to double the number of samples has to be double the frequency. So what does that mean in English? That means if you want to accurately construct the data along an array like this, you need to take at least 2 samples from every voxel, actually, if you want to guarantee accurate reconstruction or an accurate representation, a minimum of 2. That's the theoretical limit, basically, and I think that's really what you're asking is, what is the limit? When does my accuracy break down? And how can I know that for sure? You can use the Nyquist limit to guide you. And I could talk about that more, maybe at the end of lecture. But it's a great topic. I happen to like it for some reason. Well, I know why. It's because does anybody remember being like a child and you're trying to erase those memories. But being a child and being stuck in the car with somebody driving, probably like one of your parents, and then looking out the window at the other cars and noticing that when you stare, I'm revealing maybe a not so proud side of myself, but when you stare at the other cars, especially the wheels, that when you look at them, at first they look normal, but as they spin, at a certain point, it looks like they start turning backwards. Does anybody notice that? Am I the only child probably staring at the car when you're going, why does it, that is so strange, why does it look like...
I haven't noticed it staring outside the cars, but watching Formula 1, you notice that. It's the same idea there. It's the same idea there. That is tied also to the Nyquist limit. That's why I bring that up. So your brain or your vision system can sample a roughly 20 frames a second. That's roughly what it processes, 20-ish. So so that means if something is moving at more than that fundamental limit, faster than that fundamental limit, it's not going to appear correctly. It's not going to appear accurate. Oh, is that why the Hobbit looked weird?
And this is why, like, a film is 25 frames per second, to make sure that your vision system cannot detect that it's not a continuous signal, right, that you're seeing. And that makes the tires look like they're going backwards. I don't know, if we have time, I can draw a picture of why that is. But you can imagine a clock, you can imagine a clock. I did bring a marker. It doesn't matter if you concentrate on the minute hand or the second hand or whatever. But if you imagine the second hand going around, it's got a period of 1 minute, right? And imagine you want to do a time-lapse film of that and make it look like it's going forward very quickly. You have to make sure you sample the period of the second hand more than twice a minute. So if your next photo appears at 20 seconds, your next snapshot appears at 20 seconds, and so on, at 20 seconds, if your period is 20 seconds always, period, Then, when you stare at that clock in the time-lapse version, it will appear as if it's moving forward. It will look correct. But as soon as you hit the 30-second clock, at that, if your next snapshot is at the period of 40, it's going to appear like it's going backwards. If you're in the time-lapse photography, so imagine it's gone around to 40, and then you take a photo of it, it's going to appear like it's going backwards in your time-lapse photography. Anybody knows what happens? I can't believe we shouldn't be talking about this for so long. Anybody knows what happens if you take your photo at exactly 30 seconds? It looks like it's standing still, exactly. Or just flipping back and forth between, assuming you take your first one at 0. And that's the Nyquist limit. The Nyquist limit is you must sample your signal, in this case it's the clock turning, at least double the frequency. That means at least twice per minute in this example. Right. Here it means at least twice per voxel. So it applies to basically everything. It's kind of a standard topic. But that is the long answer to your accuracy question. But it's good to know. I think it's great to know. Like I always wondered that. And I still look outside, like out of windows, and I still just stare. But now I know why it's happening. Has anybody ever heard this expression? Like, if you see a person just sitting by a window and staring out, they look like a crazy maniac. But if they're smoking a cigarette, they look like a philosopher. It's so weird, but it's true.
That's why you smoke. That's the reason you pick it up, so you can stand outside and stare.
Yeah. Okay, so remember that slide is in 2 dimensions, but the real ray tracing is in 3 dimensions. Right, so what we were just looking at was bilinear interpolation. That means 2 linear interpolations. But in 3D it's trilinear. That means 7 linear interpolations. 4 along the one direction, 2 in another direction, and then 1 in the last direction. Right. So we did talk about that already a few lectures ago. Now we didn't really talk about compositing yet. And so what is compositing is you can think of adding, to compose something, right? Oh, I guess I didn't find a definition of it in my books. So when I have books on database, and I always look for a definition first. So apparently I didn't find one. The sample-by-sample accumulation of color and opacity values along a ray as it traverses volume data. So that's a definition of compositing. Now, there is another term here that is confusing, and it's called kernel, right? Or a convolution kernel. It has 3 names to be as confusing as possible for the whole world. A kernel can also be called a convolution kernel. It can also be called a convolution filter, meaning 1 or 2 dimensional images that are used for computing the weighted average of pixel images. So that just means a sampling technique that uses a weighted average in English. Right? That's what it means. And to be confusing, it's got 3 different names. And I'll repeat that. I'll repeat that if this, you know, when that comes up, to try to make it clear. So as you cast a ray into a volume, right? Imagine you're casting a ray into a volume. You can composite or add the colors and opacities from the front to the back, or from the back to the front. Right? From the back to the front was the original way of compositing, and then front to back is an optimization of it. It's a way to accelerate the compositing phase because of early ray termination, which hopefully I'm going to demonstrate. And you'll have to memorize these formulas for the test, because that's question number one, like what are the formulas for? You guys are lucky you don't have to memorize any formulas, because I could rarely memorize non-trivial formulas when I was a student, so therefore I'm not going to pass that punishment on to you. But you need to be able to recognize formulas, like if you see one, be able to say, oh, I know, I can guess what that is, or I know what that is. Okay, and then I have theoretically a demo. Let's see if this works. It's going to be exciting. Okay, so this is an example of casting a ray into a volume. And here we're sampling the volume data, and every time we sample the volume data, we compute the color and the opacity. That's what this is, the color and opacity in image space. So let's see. So that's us putting the ray, casting the ray into the volume. And notice at the beginning, there is no color and there is no opacity, because we haven't hit the data yet, the data that we're interested in. That's going further. Further again. Now we've started to enter the volume or the data, the interesting parts, and we've computed a color and we've computed an opacity. Right. And it will increase as we continue through the volume, especially the opacity. Now look what's going on. When the maximum opacity value is 1, you can't get a higher opacity than that. That means if I sample beyond that point, it doesn't affect the image. So therefore, I can terminate the ray. And that's what's meant by early ray termination. Notice that the color is staying the same after I hit the opacity of 1. That's one ray. That's an example of, that's a demo of one ray being cast into the volume and then sampling color and opacity along the way.
But the color changes. Or is it just projected? Isn't that purple?
Yeah.
Yeah.
No, the color doesn't change.
You're right with the sample, you've got the purple circle.
I don't see any change. Anyways, I don't see any change actually.
We're off the image that you sampled, in the example, on screen.
Mm-hmm.
You've got the big brown block.
Yeah.
And there's a purple circle.
Yeah.
You're saying that was a colour change there. I'm saying the piece there.
If you terminate the ray early, you're not going to find the other color.
That's right, exactly. So when the opacity reaches 1, you cannot, it doesn't help to go any further.
Because you're not going to see through.
Yeah, you're not going to see through. You're not going to see beyond that, exactly. exactly. Thank you for saying that.
So from
That's what I'm trying to say.
perspective, you're simply not going to see the thing.
Exactly. Unless, well, this is an advanced question, what would you have to do in order to see that purple thing?
Other side.
Yeah, you could rotate, very good answer. It's not the one I was thinking of. It's correct, and it's a very good answer. The one I was thinking of was adjust your transfer function
Or to just reduce
to change the opacity, which data gets the higher opacity and byte, and so on. That's one ray, by the way. And there is an image of all the rays, like, and then the accumulation, so to speak. So that's like, it's supposed to be a helpful demo. I think it is a helpful one. That was exciting, wasn't it, the demo? Yeah, so back to front came first, and this is really from computer graphics. And this came later as a way to accelerate the ray casting or the ray tracing computation. As soon as the opacity reaches 1, you can't see beyond that data, and therefore you can stop sampling it. You don't need to keep going and keep sampling. Here are some examples. Right, so these looked like isosurfaces, really. They look like isosurfaces, but they're not as smooth as isosurfaces in some ways, right? There's some aliasing. Actually, the projector resolution is not as good as what I'm seeing on my screen. It looks clear, crisper on my screen than here. But what's my point? You might look at this and think, well, wait a second, aren't those surfaces? The answer is yes, they are surfaces, but they're not composed of triangles. They are representations of surfaces, and they're generated using Raycasting rather than, say, marching cubes or some triangulation algorithm. The Raycasting we just saw. So yeah, this is one transfer function. This is emphasizing the gradients, by the way. And then if we peel away that layer, we get another layer also emphasizing gradients. Right? So you can generate very similar imagery. And there are some more examples with color this time.
Basically, when you put it on the screen, everything looks like a surface. So the surface is more technical, as in made of triangle, while everything is not.
Yep, it's implementation. It's an implementation like.
It's not a visual definition. It's just the way these images made.
Yes. So, by the way, that leads us to our next question: is why would you choose this over, say, marching cubes to generate your surfaces or to look at surfaces? Anybody remember that? We did mention it, but it's good to mention it again very explicitly. It's a good test question. I like to talk about tests when the attendance is low for some reason. That's my favorite time.
Isn't Raycasting more precise in its interpolations?
So Raycasting, remember, it allows us to give objects a thickness. So real objects have a thickness to them.
Like if you did this with marching cubes, you wouldn't be able to peel off layers. You would have to redo it, wouldn't you?
With those different layers in marching cubes correspond to different ISO values. So you can do it, but yeah, you'd have to change your ISO value or compute multiple ISO surfaces or make one semi-transparent. You can play with the opacity, but you have to run the algorithm multiple times. You have to run it once for each ISO surface. But, so real objects have a thickness, that's one reason. But real data has an uncertainty too. We never talk about it. But like when you measure something, there's uncertainty associated with that measurement. If I tell you it is -5 degrees in this room, there's a ±1 there, or some plus-minus thing. Every measuring device has error or uncertainty associated with it. And so this is saying, look, I know I can reflect the uncertainty. It's not infinitely precise. A surface is infinitely thin, so it's infinitely precise. It implies certainty. Right? It's like saying this is exactly correct in what I'm showing you, and there's no room for error. Whereas here, there's some thickness, there's some fuzziness, right? There's some error. And the error is associated with the measuring device. It's supposed to be there, actually. If you get data with error, probably you want to be aware that the error is there. But you don't want to just magically have the error disappear.
So raycasting is more realistic.
Raycasting is more realistic, exactly.
Because if you had done that with marching cubes, you wouldn't have that error. It's really smooth it out.
Yeah, some of the error is lost. The marching cubes algorithm always forces a binary choice. Either you're inside the surface or outside the surface. This one is saying, okay, you could be somewhere between this voxel and this voxel. Like it's not so binary, like on, off. You know, it's associated with an opacity, and the opacity can be anywhere from 0 to 1 and all the values in between. Does that make some sense, hopefully? So yeah, that is a big reason for the raycasting. And I think I have some little demos, maybe? Maybe? I think so. Yeah, so this is showing volume data, but the objects have a thickness, right? It's a tornado with thickness. Right? Tornadoes don't have surfaces, right? They have volumes. And that's a time-dependent volume data, by the way. That's changing over time. Do I have another one? That might be the only one I have today, right now. Oh, here's another one. By the way, you can see aliasing artifacts in this one. But so now you know, after today's lecture, that aliasing artifacts appear whenever you violate the Nyquist limit. So you can also say that. Means your data sampling is not high enough to accurately reconstruct the signal or whatever it is you're looking at. I managed to get through the whole lecture without putting on my sweater. But I can tell you I'm cold, like, I want to put it on now. Yeah, we could all store our food in here, actually. It was like free refrigeration. Okay, any questions? We'll stop for today. Yeah, happy Monday. Happy Monday.
In the demo, you put the array, it samples through the first bit, and the opacity doesn't reach 0 until it changes color. So then we just stack, like it takes the cubes. So it looks like a cube.
I'm not sure I understand your question. Let's bring it back up. So the question is, yeah?
This is data.
That's right, this is data. Yeah.
Let's say you take it from here. First it's going to reach like 1. This is going to be 0.02. And if before the 1 is reached, it goes into the next color. And what about here?
It will keep increasing. So every time it goes further, the opacity increases.
Okay.
Unless it's like a completely translucent material, you know, like a space. But if it's sampling non-zero data, then the opacity will always increase. Generally, like unless you play with your transfer function, you could play with your transfer function and say the opacity of this material is very high and this is very low. Or you just make it kind of uniform. But yes, if it's, imagine it reaches here and your opacity is only halfway full, so to speak, and it hits the blue, then this thing will start changing color it will start being a mixture of the orange and the
Mixture.
purple. That's right.
Because at the end there was a half circle with all of the arrays.
Yes.
Basically this is going to be this color, and then when you go to the center it's going to change from here to here.
That's right, that's right. This example is, you know, it showed that because of early ray termination. All of those rays reached their
Opacity.
yeah, well, there's only one in this example that reaches the
Does it mean anything that these two are different colors?
No, actually, that's a good question. No, it doesn't. Yeah, this is just trying to show, like, it's like a graph of opacity. There could be another line here where it reaches 1, and it's just trying to say, like, okay, here it never reached 1, and here it almost reached 1, and then at some point it reaches 1. There could be a 1 line. But it's really a line graph of the amount of opacity along the ray, each ray. Yeah, that's a good question. We should have asked that in class.
I think someone did, because someone did start trying to have a question about like different colors.
Yeah, we were thinking about this, the difference in
The different colors, yes, that's true. I didn't really explain this aspect. I just sort of thought it was implicit in the way that thing was moving.
Yeah, because when you're sat out there, you can't see the difference in those two
Oh,
colors.
okay, yeah.
So like sort of one brown there and then some.
Okay, yes, I can see where that could be confusing. Yes, definitely. I'm glad we did that demo. Yeah.
Is this supposed to look like this? Because as you mentioned, this should be basically a line. If this has reached, like if from here it's 1 opacity, this shows that it hasn't reached the full opacity. And
That's right, that's why I was saying it would be nice if there was a third line in here that said, like, this is the maximum opacity line of 1. And this just goes to show that there are more samples along the ray, but they don't contribute because they've been cut off at the 1.0 threshold. Yeah. Yeah.
On assignment 1, a data set isn't necessarily just like a set of data, is it? Like, because I was looking through Sally, and Sally's just, no, Sally 2, sorry. And Sally's just a method. So,
Yep, Sally is what we call analytical data sets. That means you input a position and a time. In your case, you would just choose 1 as a time, it's always the same.
It's always the same.
Well, it doesn't have to be. You can change the time if you want, but you just add some complexity. If you don't have to change the time.
What I do is I rewrote it in Java.
Okay.
So, because I'm better with Java than with C.
Good.
Replace the pointer with an array list.
Yes.
And then at the last 3, I need 3 explicit values to the array list.
Yes.
And then print that and then write that to my own file.
Yep.
So I'm guessing. So it's right that there isn't any specific number to plug into. Because I tried plugging in 256. I think you suggested it on one of the ends, and it took so long to process it. This is relatively this long.
So I would try different numbers. I would try like 64 cubed, and then 128 cubed, and then maybe 256 cubed.
And then guess what I'm going to do next is format what outputs, and then use that data in one of the data-first ones, and it's going to show some kind of shape.
Correct. Correct.
I just wanted, because I looked at it, I expected like a table of data.
No, it's about a shape this time. And then looking at the shape and then trying to figure out what it is. Yeah. If you see any shapes, that's a good sign. If you see random noise, that's not a good sign.
Yeah. Try different numbers, please.
Yeah. And like, you can do different things. You know, those are vectors. So like one strategy is to make a smaller data set, but the other strategy is to make, okay, what does it look like in 2 dimensions? You can take one slice, for example, and just try to look at a slice.
Yeah, I cut out the set component and just have the X and the Y.
Exactly. And then you can also try to figure out by hand what those vectors look like. You can actually look at the data and say, okay, this is the X component, this is the Y component, so the vector should look like this.
Yeah.
And then see if it really does in whatever software you're using. Like, is the vector pointing, like, is it behaving the way I expect it to based on my little notes, you know, my little drawings and stuff?
Yeah.
Yeah.
Because I don't know if you've ever seen that, I just remember because of the clock example. I saw this video the other day of someone filming a helicopter taking off.
Exactly.
But it matched the frame rate to the frequency of the roller, so it didn't move at all.
Yeah.
So she saw this helicopter just floating in the air.
That's cool.
And it's off.
Now you know why. Now you know why that happens. I always wondered that when I was a kid. I was like, that is weird. Why does that happen? You know?
Yeah, I saw everyone's done it, so I wrote down.
Have you guys ever watched a video of a bass player that strings on a bass?
No.
Check that out one day. So the bass strings vibrate at a certain frequency, right? But in video, the video is not rolling fast enough. It's not sampling the string fast as quickly as it's vibrating. So the string appears to slow down in the video. Just you know, go to YouTube and hit like bass strings, video of bass player or video of bass strings, and you'll see it's so cool. Because they slow down. They look like they slow down, and it's like, oh, it looks so psychedelic. Yeah, it's cool. It's cool. Any other questions? Happy Friday. Happy Monday. See you on